All right, the extreme value theorem. This is not one that you've called by name a whole lot necessarily. We use the extreme value theorem whenever we're trying to find like the absolute maximum versus the absolute minimum on a closed interval, okay? So what the extreme value theorem says is if f is continuous on a closed interval from a to b, and it must be closed, we must include a and b, then f is guaranteed to have both a minimum and a maximum. And we're talking about absolute minimum and absolute maximum on that interval, okay? And then just definition of minimum and maximum, f of c is the minimum if f of c is less than or equal to every other f of x in that interval. Same thing for maximum, okay? So we're used to finding relative extrema using the first derivative test, but we apply the extreme value theorem instead of the first derivative test whenever we're given a closed interval. So you're still going to use the derivative to find the critical numbers, but we go back to the original function, whatever we're trying to optimize, maximum or minimum, and you plug those critical numbers and the endpoints back into the function to choose the value that is the most. You're going to create a table of values. That's always going to be your justification. We've seen this with the rate in and rate out problems and those sorts of things, which we're kind of going to come up to in the next couple of units. All right, so this we've talked about before. I would always write your answer in the following way. So I would make the statement that the absolute max or min is f of x equals blank at x equals blank. This way you're giving both the value and the location. So if you're not sure, is it asking where or is it asking what? You've at least clearly stated both things, and you're going to make sure that you answer the question correctly regardless of how it was asked, okay? So number 4 says, determine the absolute extrema of f of x on the closed interval from 0 to 3. So once again, the fact that it's asking for absolute extrema and the fact that it's giving us a closed interval is what tells us that we need to be using the extreme value theorem. So we need to start by determining the critical numbers on the interval from 0 to 3. We don't care about them if they're outside of that interval. So we start by taking our derivative, which is going to be 4x cubed minus 16x. We can factor out a 4x, and that's going to give us x squared minus 16, which is x plus 4, x minus 4. Oh, no, I'm sorry. I'm doing too many steps in my head. Let's write this up. So this is going to be x squared minus 4, not 16. So we get 4x times x plus 2, x minus 2. So our critical numbers are going to be wherever this is equal to 0. So we are going to get x equals 0, x equals negative 2, and x equals positive 2. We can ignore x equals negative 2 because that is not in the closed interval from 0 to 3, which is the only place that we are looking, okay? So we now need to set up a table of values looking at x and f of x. So we're not plugging into the derivative. We want to know the actual value of the function. So 0 is a critical number and 2 is a critical number. And then we also want to include the endpoints. Well, 0 is already on the list, but we also need 3 because it's an endpoint. And if we plug those into f of x, we get 0, we get negative 16, and we get positive 9. So just by looking, we can see that we have an absolute minimum here and we have an absolute maximum here. Now make sure that you answer the question clearly. Just writing down min and max like I did there, that would get you no credit. You got to answer the question very clearly. So my final answer here, I would say that there is an absolute min of f of x equals negative 16 at x equals 2, and I would say the same thing, absolute max of f of x equals 9 at x equals 3. That is how we apply the extreme value theorem.